Hello and welcome to today's webinar on IR Detector Sensitivity. My name is Desmond Lamont and I'm the Director for Global Business Development for the Teledyne FLIR Research and Science vertical. Before we get started, I wanted to invite you to enter questions through the webinar portal. I'll try to answer these as time permits, but rest assured, you will get an answer to your question. So just a brief agenda here to provide context. I'll briefly review IR detector types, and then we'll dive deeper on the topic of sensitivity, including how it's measured, what affects camera performance, and so on. To wrap things up, we'll talk about how sensitivity performance affects your applications. Just as a reminder, this is one of a 5-part webinar series covering the 5 things you need to know about IR detectors for research applications. Please be aware that all of these sessions are going to be recorded and available for on-demand viewing on our website. Currently, session 1 covering the topic of speed is available, so feel free to check it out and share it with colleagues that you might have missed it. So, detector types. What IR products does Teledyne FLIR make for engineers and scientists like yourselves? Well, our cameras operate in the infrared spectrum, located at wavelengths longer than the visible spectrum that most of us are used to seeing with our own eyes. At FLIR, the infrared spectrum begins roughly at 1 micron, with the true thermal bands beginning around 3 micron. If we move from left to right after the visible spectrum, we have shortwave, midwave, and longwave. At FLIR, shortwave is 900 nanometers to 1.7 micron. Due to its proximity to the visible spectrum, FLIR is great for exploiting characteristics of material that we're used to in the visible spectrum, such as imaging through glass. Alternatively, FLIR detectors can also see through surface coatings like paint to inspect the materials below and see through atmospheric constraints like haze. Another aspect of being close to the visible spectrum is a really high noise floor for thermography applications. So factory calibrations, if you can even get them, typically have a starting point of 400C, maybe even higher. At FLIR, it's 400C. Next is midwave. Midwave is the standard range when it comes to most radiometry and high-performance thermography applications. These detectors are exceptionally sensitive at typically better than 20 millikelvin NEDT, which is the sensitivity measurement. And for many applications, there's enough energy to adequately fill the detector wells to run at frame rates of 1 kilohertz or greater. Finally, we have longwave. There are a few different detector technologies that address the longwave. It's also an interesting waveband because there are a lot of photons out there. This enables better measurements at colder temperature, the use of cheaper detectors, and it allows for cryo-cooled options that achieve very short integration times in comparison to their midwave counterparts. Another interesting feature of the longwave is that you experience fewer solar artifacts and solar glare. At the end of the day, all IR wavebands are going to be complementary to one another for the unique capabilities or properties found in each range of the spectrum. For those of you unfamiliar with IR detectors and subsequent cameras, the left side of the chart shows common representation of microlometer-based systems. These range from very small sensors like the FLIR Lepton in the bottom left to the more common handheld cameras used by many people for quick evaluation of a circuit, motor, or a relatively larger, slower target. On the right side of the screen are examples of cryo-cooled cameras, also called photon counters or quantum detectors. These systems are much higher performance and are typically the models of choice for engineers and scientists due to their flexibility and access to the raw data. I mentioned cryo-cooled detectors and bolometers in the previous slide, but there are quite a few detector materials available for the cryo-cooled detector that you see here. These range from INSBE to MERCAD to SLS and so on. The good news is that the majority of applications have basically standardized on the use of InGaAs for SWIR, INSBE for midwave, and bolometers for most longwave applications. I will say that in the longwave or any waveband, choosing the right detector, whether it be bolometer, cryo-cooled, etc., is really going to depend on your specific application requirements, and having even basic knowledge about the differences between primary detector types on the market is really going to assist you in identifying the most appropriate option for your application. We've reviewed some core differences between detector design and the speed webinar prior to this one, so be sure again to check that out for more information. As always, I recommend speaking with the local sales engineer though to identify any kind of final configuration options to meet your application requirements. So the topic at hand, sensitivity. So what do we mean by sensitivity? Feelings? No, not this kind of sensitivity. Sorry, Dawson, you'll need to take that back to the creek. Thermal sensitivity is what we're discussing today, also called NEDT or noise equivalent temperature difference. This is a key figure of merit used to qualify thermal cameras. Unfortunately, NEDT is commonly confused with aspects like accuracy and minimum resolvable temperature difference, but those aren't correct. NEDT is actually a signal to noise figure that represents the temperature difference that would produce a signal equal to the camera's temporal noise. An easier way to think about this would be to consider it the temporal noise floor of the camera expressed as an equivalent temperature value, or maybe even easier, this is where the camera can no longer tell the difference between noise and a temperature measurement. So NEDT is calculated by dividing the standard deviation of the temporal noise by the response per degree or responsivity, and it's going to be expressed in units of millikelvins. The value, it's not an intrinsic property of a given camera. It only corresponds to that 2D mean temporal noise in very certain specific conditions, expressed as an equivalent value of temperature, meaning that as you change the conditions, that value will change. Strictly speaking, as NEDT value decreases, the sensitivity of a camera is going to increase. For example, bolometers typically have a 30 to 50 millikelvin NEDT, whereas our cryo-cooled cameras are typically better than 20 millikelvin. We'll talk about this in a minute, but while 20 millikelvin and 30 millikelvin sound close, they're actually quite different in terms of imaging performance. Also, you can compare NEDT values across different detector types and vendors, but be aware that NEDT is calculated differently for different detector types. So while you can compare across different detectors and vendors, I would really only use it as a general comparison spec, because the system performance in your application is what really matters, and how they measured that NEDT really matters. Beyond detector differences, the value is really a function of the camera's F number, which dictates how much energy is permitted to hit the detector over time, the integration time or exposure time, how long we let energy hit it, and the temperature at which the measurement is made. As you adjust any of these individual aspects, you can achieve a better or a worse NEDT. Since this measurement is really related to noise, it would be good to talk briefly about sources of noise for IR detectors. First, let's identify types of noise. Well, this slide depicts image captures from a cooled photon counter camera. Both photon counters and bolometers experience temporal and spatial noise. It's just easier to get pictures of them on a cooled camera since we can turn off all the corrections. In the image on the left, we have temporal noise. Temporal noise happens randomly per pixel over time, as opposed to spatial or fixed pattern noise that does not change with time. Temporal noise, it's the most noticeable noise in a system that has a good uniformity or good non-uniformity correction. A non-uniformity correction, if you're not familiar, is performed to align the response of each detector element or pixel in the detector array so that they report out the same counts for a given energy. This is done before any calibration is performed on an IR camera. When a well-nuked camera, that's just the abbreviation of non-uniformity correction, NUC. So when a well-nuked camera is pointed at a very uniform IR source, the image, it looks a lot like the snow that you'd see on an older television tuned to a channel with no broadcast signal. Since all the pixels are reporting similarly from the nuke, each pixel's digital count value is going to fluctuate randomly with time around a mean value. If you look at the right, spatial or fixed noise, examples of that are going to be darker corners from cold shield shading or vertical bars in the image caused by differences in the ROIC or readout integrated circuit column amplifier offset. As mentioned, a good non-uniformity correction will clean up the spatial or fixed pattern noise. Now let's touch on sources of noise to understand some primary contributors to the NEDT measurements. Most IR applications are taking place in a background limited regime where the image noise is dominated by random fluctuations in the scene energy. For photon counting cameras, this is called shot noise, quantum noise, or scene noise, and could be considered similar but not exactly the same as the white noise, primarily Johnson noise, in bolometer detectors. These are similar in that they're both random and independent of frequency, so white noise. These two types of noise dominate the overall system noise for photon counters and bolometer detectors. Now, scene noise, it's the square root of the mean of photoelectrons generated by radiation from the scene. What does that mean? Why is it important? Well, for starters, it's always there. In practice, if looking at a uniform scene, the noise can become quite a large contributor to the overall image and signal. Johnson noise, it's a type of white noise and shouldn't be a surprise for those of you more familiar with bolometer design. The design of bolometers is going to rely on applying a bias voltage to a detector element to read the change in resistance experienced from the incident radiation striking the element or the pixel. Johnson noise explains how conductive materials with resistance temps above 0 will generate a current with voltage. Since bolometers are sensitive conductive elements, you can see how this could be a large contributor to noise in a bolometer system. The other noise sources that you see listed here, they're typically negligible to system performance in the vast majority of applications. So for the sake of brevity, we're going to move on now to what sensitivity is not. As mentioned, NEDT, sensitivity, it's not an accuracy measurement. You'll notice that most IR camera data sheets show how accuracy specifications, they'll list those typically as a plus or minus 2C or 2% of the reading, something like that. The specification, it's going to be the result of a widely used uncertainty analysis technique called root sum squares, or RSS. The idea is that you're calculating the partial errors for each variable of the temperature measurement equation, square each of those error terms, and then add them together, take the square root. Those partial errors, those can result from several variables, including the emissivity or surface emissivity of the target, reflected ambient temperature if you've got a low emissivity target, transmittance, atmospheric temperature, and so on. The next would be minimum resolvable temperature difference. NEDT is not the same as MRTD. The term here is resolvable. That's what you need to pay attention to. Minimum resolvable temperature difference is an observable spatial measurement, typically performed by an operator or technician to determine the minimum temperature difference at which the 4-bar target that you see here can be resolved. The MRTD, it's used to show an operator how effective a system is at discerning details in a scene, and I consider it more of an estimate to resolution capability, and it can really be subjective to the operator. So not the same as NEDT. And finally, we have D-star. It is not D-star. We don't use D-star here at FLIR, Science and Research vertical. We don't use it because it's an obsolete figure of merit, which was used to compare single element detectors. It doesn't work well for comparing focal plane array type detectors that we see here. It's been replaced by NEDT by the industry because there are really no assumptions or approximations in the calculations of NEDT. NEDT is an empirical, straightforward, easy to understand measurement, whereas a D-star calculation requires the noise bandwidth or noise spectral density, and those really can't be measured. So they're assumed or approximated to get a D-star measurement. So NEDT is not accuracy, it's not minimum resolvable temperature difference, and it is not D-star. Now that we know what NEDT is and what it's not, let's talk about how it's measured. This is going to be a lot of information, so buckle in. First, we're going to discuss how it's measured on cooled photon counters, then we'll talk about the bolometers, because as I mentioned earlier, it's different. At FLIR, the NEDT on cooled cameras is measured at 50% nominal well fill, a 298 Kelvin background, plus or minus 5 degrees C signal. What this means is that we dial the integration time or exposure time in to see 50% well fill. But you might ask, if you're not familiar with these detectors, what is well fill and how do we know what that well fill is? Well, check out the speed webinar for more details on the detector design, but at a high level, cooled camera detectors capture scene energy and integration capacitors, and the well depth of the capacitor dictates how many electrons we can capture. So regardless of the well depth of a given detector, these are 14-bit cameras, so a 14-bit depth camera is going to produce 2 to the 14 or 16,383 A to D count possibilities. At 50% well fill, we're talking roughly 8,500 counts or so. 298K. The 290K background, that is just the target temperature that we're going to use for the measurement. 298K equates to 25C, if that helps you. The target is the black body temperature source, like you see imaged in the bottom right of the slide here. To summarize, we're dialing in that integration or exposure time to hit roughly 8,500 count well fill for this measurement again. Why is this important? Well, as you increase that well fill beyond 50% or below really, but if you move it beyond, you're going to capture more electrons and inherently improve your signal to noise ratio. You can also perform the measurement at a higher temperature target and accomplish the same thing because you'll have more energy in the scene. So it's important to know how that figure is measured to properly compare cameras and detectors. Measuring NEDT, it's relatively straightforward with a cooled camera because it's easy to get to the raw A to D counts coming from the detector. At a high level, a 2-point non-uniformity correction is going to be performed to obtain a uniform image like we just talked about. Then 3 sets of data are taken using the camera's digital data output. For the nuke, or non-uniformity correction, the black body is set to 25 degrees C. The camera is placed as close as possible to it with no lens, so about 2 to 5 centimeters or so. And you might say, why no lens? Well, no lens because we don't want to bake focused details of the surface of that black body into our non-uniformity correction. Remember, this is to align the response of all the pixels on the detector to report the same for the target temp. For the first data set, we're going to set that black body temperature. Now that we've got that nuke done, we're going to set that black body temperature to 20 Celsius and collect 64 sequential frames of data. Take the average of those frames for each pixel to build an array, and that array is going to represent the response at 20 C. The units of this measurement, again, are A to D counts. For the second data set, we change the black body temperature to 25 C, collect 128 sequential frames, take the standard deviation at each pixel's value over the 128 frames, and place these standard deviations into an array, which then represents our temporal noise, again in A to D counts. For the third data set, we set the black body to 30 C, and just like the first data set, collect 64 sequential frames of data. We again take the average of those frames for each pixel and build another array, this one representing the response of the camera at 30 C. The units, again, A to D counts. So now we have 2 response arrays, one at 20 C, one at 30, and we have a temporal noise array that was captured at 25 C. By subtracting the 20 C response from the 30 C response and then dividing by 10, we get a final responsivity array with units of counts per degree. By dividing the temporal noise array by that resulting responsivity array, it's going to produce an NEDT array with units of kelvins. Taking the average of all the pixels in the array, neglecting any bad pixels, and multiplying by 1,000 is going to give us that figure of merit in millikelvins. So for bolometer type detectors, we see a less rigorous measurement process. And again, that's due to the trade-off in design of bolometer versus cooled photon counter. The bolometer, it's optimized for highest performance that can be reached at the lowest possible cost. So there's a large amount of signal processing that occurs at the detector hardware level itself. Because of all that signal processing going on, access to low-level data and controls is pretty rare. Also, due to the bolometer design, there's no customizable integration time. So we're really measuring NEDT here with a fully calibrated camera set to an applicable temperature range for the given target, in this case, 30 C. Instead of capturing the 3 data sets that we captured prior, we capture a single data set of 128 frames while staring at a 30 degrees C black body source. We then stack the 128 frames and take the standard deviation of each pixel to make a single frame. The median of this frame is the bolometer NEDT value multiplied by 1,000. Once again, gets us that value in millikelvin. An example of the calculation of one of our older handheld cameras is on the right. As you can see, the mean is shown here, but it should be very comparable to the median based on the curve in the chart that you see. This specific model had a feature called noise reduction. That's what that NR on is referring to. That effectively averages more frames over time, and that really helps to remove additional temporal noise, which obviously helped the camera achieve an effective NEDT of roughly 25 millikelvin, which is pretty impressive. By the way, that's not what was on the data sheet of this camera. That's just what was in the specific offhand measurement here. If you did the same measurement process with a cooled camera, you'd actually, from a curve perspective, you'd see a tighter base to the curve, and that's due to a more aligned pixel response achieved from those detector types. And that percolates into the final imagery that, again, looks a lot more crisp and clear. We've just reviewed how each measurement is conducted, but again, the main takeaway is that changes in how the NEDT measurement is performed can really drastically affect the outcome. For example, if a spec sheet stated that the measurement was performed at 50 C and showed a similar sensitivity as a camera NEDT measured at 30 C, I'd really ask more questions about how that measurement was performed, and I'd really want to see the camera in action to properly compare. Likewise, if minor adjustments were made to the integration time on a cooled camera that caused just a few hundred lesser A to D counts, or let's say that fewer frames were collected for averaging, you'd see NEDT move in the opposite direction and look much worse. So just remember, this is not an intrinsic property of a given camera, but a measurement under very specific conditions. So now you might ask, well, how does this actually affect my specific application? Well, first I'll start off with the handprint demonstration. If you've ever been introduced to a thermal camera in person, you've probably seen the handprint demo. For all its practicality in nearly any setting, the handprint demonstration is very exciting. I mean, who knew that just briefly touching a wall could transfer so much heat? This is really where you remind yourself of just how little heat was actually transferred and just how sensitive these cameras really truly are. In this demo, you're going to see how the photon counter on the top compares with the bolometer at the initial touch. The bolometer is displayed on the bottom. You can see so much more detail on the photon counter image because each pixel is going to be reading smaller steps in temperature versus the noise, whereas the bolometer cameras experience a much harder time due to its more difficult signal to noise. Over time, 2 minutes to be exact, as you move to the right, you can still very clearly see the handprint with the cooled camera. However, the handprint on the bolometer image is almost at the point where you might not even identify it as a handprint at all. And that's really the challenge that we're talking here when you're talking about comparing camera systems, whether they be two photon counters or bolometers, and you're comparing that NEDT. The handprint for the bolometer here, it's beginning to reach a temperature value where the camera can no longer tell the difference between it and the noise floor. So it's approaching the NEDT limit for that bolometer. When working on applications where you need to be able to resolve very low energy events or even transient thermal events, the bolometer-based detectors are going to have a much more difficult time, or it might be impossible for them. So let's take a look at this same thing with the in action on a more realistic application. Here we have a PCB inspection application. We're performing thermal profiling on components. On the left, we have a cooled photon counter camera, and on the right, we have a bolometer detector camera. Both cameras have similar resolutions of 640 by 512 for the photon counter and 640 by 480 for the bolometer. So it isn't really resolution that's creating the difference in quality of data imagery that we're seeing here, but the difference in sensitivity. With the lower NEDT, the cooled camera can produce a much sharper and clearer image, and it's just phenomenally better for measurements and decision making. Can you guess the sensitivity for each detector here? Might not be a surprise. The cooled photon counter has a specification of around 20 millikelvin. But what about the bolometer on the right? Those can vary a lot. It looks very different. So what do you think? 100 millikelvin, 50 millikelvin? It's actually only 30 millikelvin. Very sensitive for a bolometer, but just look at the difference in sharpness and detail between the two images with just that 10 millikelvin difference. If we were to draw a region of interest, which is another name for a shape that we want to use for analyzing a subset of data in the data imagery, be it a line, a circle, a box, or some custom shape. In this case, we'll make it a square since we're interested in, let's say, the larger chipset here. On the cooled camera, we have well-defined edges of the component in question. If we take a look at the bolometer side, you'd be very tempted potentially to use a different shape because of just how that imagery looks. Now that would result in a very different result for the same board, same component under the same conditions. So it's not difficult to see how slight differences in a datasheet NEDT would have affected our data potentially here. One of the most significant improvements with cooled cameras is IR sensitivity. Again, the cooled cameras, they can detect temperature changes of less than 20 millikelvin, which is less than 0.02 degrees centigrade. While an additional improvement of only 10 millikelvin over the bolometer alternative may not sound like a lot, it does represent a 30% improvement. And it produces, obviously, gorgeous thermal imagery, and it lets you detect very subtle changes. Here's another example. This is a gas mixed signal device. The analog section is at the top, digital is on the bottom. This image was captured using a high definition cooled photon counter camera with a microscope lens, generating a resolution of about 4 micron per pixel. We'll talk more about spatial resolution in the next webinar. But this device was experiencing a problem, and unfortunately, even with this level of magnification, we really couldn't identify where it was happening. This is where extreme sensitivity even needs a little help. So we recorded power being applied to the device, and then performed an operation called image subtraction, wherein you subtract the pre-powered image from the powered frames, and now you only see the delta. So you can see how having a very sensitive camera will provide smaller deltas to be measured. So that sensitivity definitely helps for identifying these very subtle changes. So here are those steps in action. This is a very fast transient event. So the first video here is a video of 2 frames. You can see there's a slight flicker of activity on the bottom of the device, slightly to the right of center, but we can't really identify exactly where it is or what it is. In order to get a more accurate location of the event, we go ahead and apply that image subtraction function. Again, this is where we subtract a reference frame from the rest of the video. You can also subtract an entire file of frames from another capture if you wanted to identify frame by frame deltas over a long period of time across the capture. Since this is a 2-frame video, we're simply subtracting frame 1 from frame 2, or again, pre-powered from powered. Since we're subtracting the frames, again, we're only seeing those deltas. So anything close to static falls away in the current color palette as black in color. And that's highlighting the location of more intense changes. This really helps us to get a very good idea of where the event is happening. You can see it there flickering in the center image. You're getting a much more targeted location and some idea of what's occurring. Then, with a little help from just some slight adjustments to how the color intensities are applied to the image, we lock in on exactly where the event is, and the engineer immediately identified the problem as a short. Is actually a short in the strip line capacitor at the very bottom. If you look at the right-hand side, it's a very small print there, but you can see the measurement values for the pixels are in deltas. So very small steps are being taken with this cooled camera, so we can identify that very subtle change in energy. Since we're able to capture such low energy, the transient events with the photon counter cameras, we were able to use those small deltas in temperature readings to identify exactly where that problem obviously was occurring. You simply could not really do that with a bolometer. They just can't measure that small of a change. So we've discussed low energy scenes and the obvious preference for cooled photon counters to meet those requirements, but what about hot scenes with lots of energy? Well, as previously noted, one way to increase our NEDT measurement was by increasing the temperature at which we were performing the measurement. So when we have a nice high energy scene, a bolometer could certainly be a viable option. What you see in the image here is a rocket nozzle captured with a bolometer detector. In fact, we have a few customers in the space industry that use bolometer detectors to evaluate rocket body temperatures during hot firing to identify any potential problems. Due to the location of a hotspot where it might occur, that researcher can then identify what's co-located with the hotspot and determine the potential cause of any issues on that rocket body. As long as there aren't other requirements that would mark the cooled photon counter as the more appropriate option, let's say high-speed events, let's say wanting to measure transient thermal events, tight synchronization with other instrumentation, specific wavebands of interest, those kind of things, the bolometer could certainly be a good option for hot scenes. I would note that most bolometers are calibrated at about a 2000 C ceiling, whereas photon cameras can be factory calibrated up to 3000 Celsius. And by the way, that's really a limitation of black body temperature sources, not really the detector. So if you fabricated or found a higher temperature reference source, you could theoretically build a higher temperature custom calibration with the cooled photon counter because it does provide access to do custom calibrations where the bolometers, they don't typically provide that level of access again. And for comparison on a high temperature scene, just for fun, here is a rocket motor plume captured with a high-speed photon counter camera. The greater sensitivity or lower NEDT is really what's providing the sharpness and clarity that you see in that image there. It was also a high-speed camera, so you can see particles, things like that flying around. But you see just amazing detail versus the lower sensitivity cameras. And this really ends the sensitivity webinar. I want to thank you all for attending, and I'll try to answer some of the questions in the chat, but we will respond to all of those that we don't get to today.